All right, I'm going to do this video a little bit differently. The answer key has already been done, so I'm just going to run through it, and hopefully this will go a little bit quicker than the ones before. Optimization is the first topic that you would be talking about from the second half of chapter 3. Optimization is just finding the best or the most or the maximum or the minimum or whatever number of words you want to use answer to optimize or find the optimal solution to an everyday situation. The steps that you're going to follow to do that: first, draw a picture. A lot of these require, I shouldn't say require, but a lot of these become a lot easier when you use a picture and can label your knowns and figure out what your unknowns actually are. Anything that says maximum or minimum or a word that falls into that same kind of category, one of those optimal words, that's going to create that's going to lead you to create your primary equation. If that primary equation has more than one variable, then you're going to have to use a secondary equation. You're going to differentiate the primary equation, set the result to 0, and find your critical numbers. You're going to eliminate critical numbers that don't fall into the appropriate domain. So you're going to have an idea of what your domain is before you go too far into the problem. Solve the equation. I would suggest using a graph for a lot of these because they're not going to be nice, but try and solve them if it's possible. Choose from your reasonable domain and then find all of your unknowns. You're going to be finding, let's say, your maximum height or your maximum volume based on height, but then go and find the height as well. Like, find everything that wasn't already existing in the problem. Question number 1. Again, you're going to see that it's all done, but I want to explain it instead of just doing it from scratch. First of all, it says, which two positive integers have a product of 361 and a minimal sum? The fact that that says minimal means that it's going to fall into my primary category, and that's usually what I jump to create right away. Sum, I just used an S. And because I don't know what these integers are, I just picked any random two variables. You could pick A and B, you could pick anything you want. Since this equation has two separate values, two separate variables, I have to use a secondary equation. The secondary equation is found from the other information you're given. I have a product of 361. My product is equal to 361. Now, how can that help me? I can get rid of one of these variables by solving it. In this case, I divided both sides by x, and I'm going to replace y with this back into my primary equation. It now will read x plus the new y, and you'll notice that the reason for the secondary equation, I now have an equation with only one variable, one type of variable. The derivative is not very difficult. Just power rule. Derivative of x is 1. The derivative of 361 x to the negative 1 becomes negative 361 x to the negative 2. Set it equal to 0. I chose to do this by hand. I would suggest that you do this by hand as well because this is an easy one. X to the negative 2 means that it's x squared in the denominator. I cross multiplied, and because I'm trying to solve a quadratic here, I took the square root of both sides. Because I put the square root here, both positive and negative 19 are my answers. However, I immediately, from the beginning, paid attention to the fact that it was a positive integer only. So my domain for x and y, both of my variables that I'm solving, I have to use positive numbers. So I eliminate negative 19. I didn't even write it down. I found x. Now, what else is unknown? I know x, I do not know y, I do not know the sum. I do know the product, 361, so I'm going to find y and the sum. Y is 361 divided by 19, which is 19, and then my sum is 38. So think of this in terms of a word problem applicable to like a shape. If I have a product, that's like area. If I have a sum, that's like perimeter. I have a product, I have an area of 361, and I want a minimal amount of, say, fencing. I have an area in my backyard, I want the minimal amount of fencing. The way to do that is have the most square backyard that you possibly could. If you increased one of your sides and you had like a long yard like that, then you would be increasing the perimeter all the way around. Okay, but the smallest perimeter would be, that's not even close to a square. You get it. So we move on to a perimeter area question. It's the same thing, except now we're talking about an application to something in real life. You have 400 feet of fencing. Now I want you to imagine that with your domain right away. I have 400 feet of fencing. I'm still going to have two variables. I've got a vertical component and a horizontal component when I draw the picture. And I drew the picture over here. Now, why would it be 200? Well, if you've got 400 feet of fencing and your vertical component is almost 0, then you would have two horizontal components to break up the 400. 400 divided by 2. The same would be true if I minimized my x here to almost 0. I'd be splitting 400 feet of fencing between two sides. Okay, but it can't actually be 0, which is why I'm using less thans instead of less than or equals. It says greatest possible area, so area is going to be my primary equation. There are two variables, so I need a secondary equation. Perimeter. Perimeter of this shape. I have two x's and I have two y's. They equal 400. Solve for one of the variables to get rid of it. I usually get rid of the y, solve for y. And then replace y with the 200 minus x that you had. Notice I now have an equation of y with only one variable in it. I distributed for easy math, and then I took the derivative, set it equal to 0. Again, it was something I could do easily by hand. Pay attention in word problems to units. This is 100 feet. X is 100 feet. X is 100 feet. So I've used 200 feet of fencing. What are my two y values? Well, I plugged it into my y equation, and I know that my y value is 100. You could also reason that as well. My other unknown is the area, the greatest possible area that I was trying to find in the first place. And that's 10,000 feet squared. Area is squared. So again, this and this problem have a lot to do with each other. If I want the greatest area and I have a certain amount of fencing, how can I cut up that fencing so that I maximize the space in the back? That's why you want to create the most square-like backyard that you possibly can. It's the most economical. All right, so now let's restrict our problem a little bit. You have a rectangle, but now let's take away one of the sides. You're going to see in other equations or in other examples where this farmer problem might have more than one pen. You're going to include maybe pigs in one and horses in another. It's not really logical, but if that's the case, put a bar down the middle and then you'll have another y component. Every time you see a vertical bar, I write y, and every time I see a horizontal bar, I write x. If I had two more y's, then that would be 3y. And if I had, more than one x here or two x's, whatever. So if I read through the problem, I'm told that it has an area of 180,000 square meters. Even though they didn't say the area is, I know that because it says square meters, that's what they're talking about. It also says least amount of fencing. So the way I interpret that is, this is my primary equation because it says least, and because it's talking about amount of fencing, we're talking about perimeter. So my perimeter is made up of two x's and a y. My area is 180,000, and that is equal to x times y. If I solve for y, this is what I get. I choose to write it in this way because when I plug it in, the derivative becomes easy. It's just the power rule. I solved both sides, cross multiplied, brought the x squared up here and actually traded the 2 down here. The square root would be positive and negative 300, but because I have a domain, first of all, I'm talking about fencing, so I know it's not going to be negative. I plugged in for y, got 600. Again, pay attention to the units. In this case, the meters. And I plugged it in to find the perimeter. The total perimeter is 1,200 meters. It's 300 here, 600 here, 300 here. I don't need fencing along the water. Now, the domain. Here's what I know. First of all, it can't be negative, so it has to be greater than 0. Secondly, I know this might seem kind of obscure because x greater than 0 could be like a very, very, very large number. But think of what pairs equal 180,000. I could use 1 for my x and 180,000 for my y. I could use 2 for my x and 90,000 for my y. But what happens if I use 0.1 for my x? Then it would be 1,800,000 for my y. What if I use 0.01 for my x? Then it's going to be 18 million. If I use 0.001 for my x, now we're talking about 180 million. And you can see that as I decrease the x, my y has to get bigger to compensate, but I can decrease the x to almost 0 and y is going to blow up. So all I know is that they're greater than 0. I can't make any other restraint from there or any other constraint. Okay? Moving on, we're talking about dimensions again, but this one's creating a box. I know in pre-calc you guys did a question like this, but now we're doing it with a calculus approach. You don't have to create the parabola and whatnot from here. Usually in previous courses you would create the parabola, you would look for the max point, and so on and so forth. But here's what I know. It's an open box. It's a maximum volume that I'm looking for, so there's my primary. And I'm given a square piece of paper or piece of material that each side is 24 inches. So this started as 24 inches, but then I cut the corners. A better visual would probably be if I dotted this all the way down. This is where I'm going to fold it based on the cut. Hopefully you guys can think abstractly and you can imagine pulling this side up and this side up, and they will only match if that corner is missing. They'll only fold up to each other if that corner is missing. So here's my hands. I cut out the corner from this side, I cut out the corner from this side, and as I fold it up, now I can create that corner. But that was only true if the X was pulled out. Now if my fingers were a little bit equaler in size, you'd see. All right, so my length and my width are the same. They're both 24 minus 2 of these X's that were cut out. And then when I fold it up, the height is the distance of those fingers. Well, that distance was X. So there's my length, my width, my height. You'll notice that there's only X's over here, so I don't need a secondary equation. I distributed, actually I foiled, simplified and distributed at the same time, and then I just had a polynomial of which I took the derivative. Set it equal to 0, and I try as hard as I can to do these by hand as much as I can. So this one came out to be 4 and 12. Why would I eliminate 12? Well, as you're doing the problem, you have to have an understanding of the domain. The domain here, if I cut this side and I increase the value of X, I can cut X all the way here. Now I can cut a big chunk out of the corner, but I can't go more than halfway because then I won't have an equal X to pull from the other side. So halfway would be 24. But I can't actually include halfway because then I wouldn't have any X value at all, or I wouldn't have any side at all. It would completely eliminate it altogether. So it's got to be less than the 12. The only other unknown is to go back and find your volume, which would be 16, which comes from 24 minus 2 times 4, times another 16, times the height of 4. Notice volume is equal to 1024 inches cubed. Cubed because it's a three-dimensional function. Three-dimensional object or whatever. Number 5 is minimizing distance. When it says closest, you can interpret that as minimal distance. So that's my primary equation. My distance formula, according to points and graphs, looks like that. Okay? Now, what are my knowns? My point, my x1, y1 is 4, 0. But I have to have a secondary equation because if I plug in x, if I plug into this and if I plug into this, I still have an x and a y, two separate variables. This variable I like to keep things in x. I just like to keep things in x. This y would have to be substituted out. Well, what other y's do I know? And that's this right here. F of x is y. This function acts as my secondary equation. in square
root of x. My domain, because I'm talking about a point on the graph, then I'm going to say that my domain is any number. I will probably come back and fix that, because if I'm looking at this graph right here, square root graph, looks like this. So I should fix this domain right now, because it says find the point on the graph, not the point on the entire coordinate plane. So because it's the point on the graph, it can't be a negative number. So my x is actually going to be different than this. I want an x value that's greater than 0, right? Because I can't take the square root of a negative number. Sorry about that. All right, so I plug in square root of x. I simplify what I have. I FOILed this. I square rooted a square, or I squared a square root. Simplify, took the derivative. This becomes a 1/2 power. Bring the 1/2 down, chain rule, set it equal to 0. I did not want to solve this by hand. It looked too complicated, but actually on the calculator it came out nicely. What I did was I put this in my graph and I just looked for my root. Find your root. My x value is 3.5. By plugging in 3.5, I get square root of 3.5, but a more understandable version of that is 1.871. So the point 3.5 comma 1.871. Now, of course, that's not exact, but it's an approximate, and it is closest to the point 40. 40 would be here, and 3.5 square root of 3.5 would be right here. So we're saying that this distance is the most, or is the least, out of all the points compared to that 40. All right, water filtration. First of all, we're talking about a cost equation. The cost of anything is always the amount that it costs for an individual item times how many items there are. Okay, so keep that in mind. This says amount dollars, amount numbers. For example, what's it going to cost me to buy 5 burgers? Well, if each burger is $1 and I have 5 of them, then it's going to be $5. Now, you'll notice that we have miles and we have feet. So you're either going to have to convert miles to feet or feet to miles. You'll see that I converted everything to feet. I'm using 3 and I'm using 4, so I'm converting everything to miles. I'm going to show you what this looks like, or I'll do it from scratch with feet in mind, but those numbers were much bigger. So if it's $50 per foot, then it's going to be significantly smaller per mile. Think about that in terms of, like, let's say that this is a foot. It's not, but let's say that costs $50. How much would it cost? $50 per foot. I think I did this very wrong. We're going to ignore this for a second. I'll do this question again. We'll come back to it. Jump quick to Newton's method. Newton's method, you need to know the derivative. This column is for your x value. This column is for your y value. This column is for your derivative evaluated. This column is to find your next number by taking your first, or technically your second column, minus your third divided by your fourth. Okay, a quick check. If I was doing your test, what I would do, just a little clue, little hint, I would take my first guess, I would store that into x, and then I would go immediately to this column. My new value is going to be x minus my function, which was x cubed plus 2x plus 1 divided by my derivative, 3x squared plus 2. And that's going to get stored back into x. All right, so look at my numbers. Negative 0.5. Now is that the actual number. This might actually confuse people. This is a fraction. These are decimals, obviously. So what I could do instead is, let me go back to storing x in. And then instead of this, I'm going to write the function, which was x cubed plus 2x plus 1 divided by 3x squared plus 2. Now this might not look like it's any different, but because I treat it like a division problem, it'll actually divide it. Alright, so there's negative 0.5. It's going to recycle the next one, negative 0.45 repeating, 453398, 453398, again rounding appropriately. I went on the graph to find the actual root, and I feel weird writing actual root and then putting an approximate, because it's an approximate root, but they are exactly the same. Now you'll notice these numbers to the right. The difference between these two numbers was that. The difference between these two numbers was that. I need to keep going until the difference is either 0.001 or less. This was slightly more than that, so I kept going. Number 2, Newton's method. Derivative, same thing. I'll pause here so you can look at your values. Okay. Number 3, took the derivative. No, I did not. This one was a little bit different. You were given an equation, and asked about the point of intersection. Therefore, we're looking for where the equations are equal. Well, the equations are equal. I could move everything to one side and treat that as y equals, but I just chose to jump to the variable. It doesn't matter if you do y equals up here and then take the derivative, or if we just take the derivative. But anyway, I took the derivative. I brought this number over and created my derivative equation. My function equation is sine pi x plus x minus 1. My derivative equation is pi cosine pi x plus 1. And again, I filled in my table very carefully, found my actual root, and technically because there were 3 roots, I should go through this process 3 times. Obviously, I did not leave enough space for that, so I wrote down what the other 2 roots were. 1 is an exact root, and then approximately 1.736484. All right, almost done. If you're trying to compare your dy and your delta y, dy is a derivative evaluated. It's a derivative with the dx pulled up. I plug in 1, I plug in 0.001, I get 0.006. Delta y is a change in y. It's what I get when I put in x plus delta x, and I put in x, and then I compare the two. My results should be pretty close, and they are. Finding a differential is really just taking the derivative and bringing the dx up. Taking the derivative, bringing the dx up. So the derivative of this product would be first times the derivative of the second, plus the second times the derivative of the first, and I put brackets around the whole thing because it all gets the dx. I chose to simplify it a little bit, a little less parentheses. There you go. Down here, a square root becomes a 1/2 power. Bring it down. 36 minus x squared to the negative 1/2 times 2x. The 2 and the 2, or the 2 and the 1/2 cancel, and I end up with this, with a dx. I didn't have to put parentheses around the whole thing because it's a product. It's implied that they are together. This one was not a product, so I had to put them together. All right, so let's go back to the question about the filtration. And I'm going to do the problem twice. We've got a couple pieces of information to keep in mind. We have $50 per foot in the water, and it costs $35 per foot on land. The picture, just very randomly drawn, it doesn't have to be exact, but I know that my plant is 3 miles offshore. I know that it is 8 miles downshore, and where we're dropping the recycling or whatever, and water filtration plant wants to develop the most economical plan that allows them to recycle their product back into the ocean. 3 miles from the shore, plant is located 8 miles down the shore and 4 miles inland. So the plant is actually back here, and this is where they're dumping things. These should connect. Okay, so the first thing I need to know is how to split the 8 miles. I'm going to put 8 minus x here and x here. Why those two? Well, think of the number, let's say 2. If I put 2 in here, that means that this side is 6 and this side is 2. So together they make 8. Also keep in mind that if I'm talking about miles, then I better be talking about money in terms of miles. If it's $50 per foot, then what is that per mile? Well, how many feet are in a mile? There's 5,280 feet in a mile, so $50 for every foot is 264,000 per mile. $35 per foot is $184,800 per mile. Okay? Now if I stick with miles, then remember, cost is amount of money times amount of number. So my cost in the water is my money times my distance. Well, my distance is the Pythagorean theorem here. It's the hypotenuse of this right triangle. So it's a squared plus b squared equaling c squared, and I solved for c, which means I took the square root of this. Hopefully in class you would have done a few of these examples so you would see where that came from. Then over here, this side would be, first of all, 184,800 times the square root of x squared plus 4. Again, if you want to see this one, if I have a squared plus b squared equals c squared, I'm going to throw in 3. I'm going to throw in 8 minus x. If I take the square root, then I'm left with c. Now, I don't want a lot of chain rule pieces, functions within functions within functions, so I'm going to simplify what's inside my radical here. Eight times 8 is 64. 8 times negative x is negative 8x, and I'm going to have that twice. And then negative x times itself is x squared. I'm going to simplify. And I'm going to write it in standard form. My son's getting a little bit whiny, so I'm hoping to finish this here pretty soon. Derivative. The 264 stays, 264,000, because of the constant multiple rule. I'm going to bring down the 1/2 from the exponent. I should have converted this to an exponent, but you remember that a square root is 1/2. Times the function raised to the negative 1/2 times the derivative of what's inside. Same thing over here. Constant multiple rule leaves that coefficient alone. I'm going to bring down the 1/2 from the power times the derivative of what's inside. This 2 and that 1/2 can cancel. I could cancel this 2 and change this to an 8 and cancel it with the 1/2, but that gets complicated. Now I'm just going to type this into the calculator because I don't want to solve that by hand. That doesn't mean that it's difficult. It just means, you know, it doesn't mean that it's irrational, I should say. But I just don't want to do it. So 264,000 times 0.5 times, and because this is a product, I just got rid of those brackets. They're unnecessary. X squared minus 16x plus 73 to the negative 1/2 power times 2x minus 16 plus 184,800 times x squared minus or plus 4 to the negative 0.5 times x. And actually, what's my domain? So my domain has to deal with this x right here. What could x be? X could be as small as 0 and as long as 8. It can include both of those. So my domain is inclusive 0 to 8. I could do my water filtration plant like I could go straight out here and then go all the way up and use all 8 for the one side, or I could hit all land if I think that's cheap and then go right into the water. Alright, so when I graph it, I'm going to end up with I should get something that's going to cross between 0 and 8. Now the reason that you can't see it, well, we can see it, the reason that it probably would be difficult to see is because we're working with numbers like 184,800. So there's going to be some weird things happening on the picture. I want to find this root. I'm not sure if you do it this way, but when it says left bound, right bound, I'm just going to type in numbers that I know this value is between. It's between 0, so I'm going to type 0, enter, and 10. It says guess. It's around 5, so I'm going to write 5. My actual, or my estimate, is 5.39. So x is approximately 5.39. That means that I'm going to be, this picture is pretty close to what it would actually look like. Now what are my unknowns? At this point I'm going to use 5.39, which means that actually this wouldn't be close. It would actually be drawn a little bit differently. This x would be right about here, and then we'd have this piece. What's my 8 minus x side? Well, 8 minus 5.39, whoops. Oh, I did it again. Is 2.61. These are both miles. What are some other unknowns? Well, my total cost. If I plug in 5.39 for x, then my cost is 264,000 times the square root of x squared minus 16x plus 73 plus 184,800 times the square root of x squared plus 16. Shoot. I didn't do 16. It's supposed to be 4 squared. That's going to change everything. Let's see how much it changes. Go back to the graph. Oh, please forgive me. We all make mistakes. Okay. Do the same thing. It's somewhere between 0 and 10. It looks like 5, and it is 5.87. 5.87. So close to what we had before, but a little bit of a mistake. All right, so what is 8? Whoops, let me store that into x. What is 8 minus that value? 2.13. What's the cost? Well, the cost is 264,000, again, times the square root of x squared minus 16x plus 73 plus 184,800 times the square root of x squared plus 16 so it's a little over 2 million. Some other unknowns that you could find are the individual lengths here, the that C value and this C value. We might as well, I'll call this D1, I'll call this D2, two different distances. Distance 1 is the square root of x squared minus 16x plus 73. That's approximately 3.68 miles. The other one is the square root of x squared plus 16, and that is approximately 7.10 miles. You could also take it as far as, what is the cost of each of those? If you really want to find everything that's unknown. The cost in the water would be this value times the 264,000 and then the other value would be this number times the 184,800. So again, it's not exact, but it's a good start. Remember, I was at first concerned about this. I thought, well, that's not right according to my picture, but this picture is wrong. This X would be way over here if we did it correctly. So it should look something more like this. That would be the most optimal, which makes sense because it's cheaper in land than it is in the water. The other thing to keep in mind is if you went through this problem again with feet, you would use 50 and 35, but you would have to convert these numbers to feet as well. So 3 miles would no longer be 3, it would be 15,840. 8 would no longer be 8, it would be 42,240. And then 4 would no longer be 4, it would be 21,020. 21,120. So how would that change our results? Well, you'd still have the same value here, but it wouldn't be miles anymore. It'd be converted to what the feet is. So I'm just going to do I don't know. I think I have it done. If you want to see it, just send a message on Schoology and I'll I'll create a video or show you a picture of how I did it with the feet. But off the top of my head, I'm not sure where that answer key is. I think I stuffed it away. Oh, I take it back. I know exactly where it is. Just be patient with me. Be patient with me. Be patient with me. Here it is. All right. 50 times really big numbers, 35 times square root with really, really big numbers. Take the derivative, and these are the two values that you're going to get when you do that. So let me do this off to the side. If it's feet, then x is approximately 31005 feet, and your cost is 971,32270. Do those numbers make sense with what we did above? Well, what's 5.87 times 5,280? Okay, now it's going to be slightly different because of rounding. We had, significant rounding up here. There were a lot of decimal places after that. So, but pretty close. And then does this cost make sense for those values? Well, if that is per mile, or if that's for the total number of miles, cost miles in mind. That's the same number I got here, so I'm wondering if I did this correctly. I'm going to ignore that altogether. Alright, but that would be the optimal feet. My son is having a nervous breakdown, so I'm going to cut this off, and if you have any questions, I will answer those specifically. Thank you, and good night.